Okay, Chapter 21, Structure and Property of Carboxylic Acid Derivatives, is a continuation of Chapter 20, where we talked about carboxylic acids. Carboxylic acids, they do have functional group of COOH. So if you look at the carboxylic acid derivative, most of them, they have a replacement group or substitute group for the OH. So for acid halide, we have the halide replacing OH. Acid anhydride, we have acetate replacing the OH. Ester, we have alkoxide, which is coming from alcohol. Alkoxide replacing the OH. So instead of OH, we have OR. And for amide, we have NH2. Amino group is replacing OH for the amides. Now, when you look at the structure for nitrile, it doesn't look like the other acid derivative because it doesn't have a CO double bond. But what makes the nitrile to be classified as acid derivative is that you get the, if you hydrolyze, if you add water to nitrile, it would change to carboxylic acid. So for that reason, nitrile is classified as carboxylic acid derivative because any of these acid derivatives, if you add water, some of them require catalyst, others don't require a catalyst. So if you add water, it's going to give carboxylic acid. If you add water to this, it would give you carboxylic acid. Same thing. When you add water to acid anhydride, it will give carboxylic acid and acid chloride as well. If you add water, it will change to the carboxylic acid. And same here, when you add water to nitrile, it will change to carboxylic acid. So all these reactions separately would count as preparation of carboxylic acid, or you can see that definition for carboxylic acid derivative are the compounds that when you hydrolyze them, it goes to carboxylic acid and another organic or inorganic byproduct. So the byproduct for acid halide is going to be HCl, but for acid anhydride is going to be a second molecule of carboxylic acid. For byproduct of ester is going to be alcohol. Byproduct of amide is going to be ammonia or amine, depends on the amide, if it's a primary, secondary, or tertiary. Okay. The first reaction that we have, preparation of carboxylic acid derivative, is preparation of esters. We talked about this before. This reaction, carboxylic acid plus alcohol, and requires hydrogen ion, or it requires a catalyst, because the leaving group here is not a good leaving group, and nucleophile is not a strong nucleophile. You have a weak nucleophile and a bad leaving group. So you must have a catalyst. H plus is going to be used, or acid would be used to catalyze this reaction, and we get ester. So the OH is going to be replaced by OR. So we have the ester. This ester is called esterification. Excess of alcohol is used. The reason for excess of alcohol is being used is that this reaction is a reversible reaction. It reaches equilibrium, And because it reaches equilibrium, if you increase the concentration of one of the reactant, it's going to push the reaction toward formation of more product, or removing the pressure from the external pressure. So that's the reason we are using extra alcohol, or excess of alcohol is used often in this reaction. Okay, pay attention to the condensed formula for acid halide, for acid anhydride, ester, and amide, and nitrile. Sometimes in the reactions, you get the condensed formula rather than the structural formula. So for each of the acid derivative, we just want to know the structure, how to prepare these compounds, nomenclature, and some of the reactions. Because you have like 5 different groups, it's covered under one chapter. It's not going to be like a lot in the detail, but at least you get an idea about how to prepare these compounds and some of the reactions as being acid derivative as well. So for nomenclature of the esters, you would name them as alkyl, alkylate. That's the general name. If you look at the molecule, the group, the R group that is attached to the oxygen is coming from alcohol. So that would be the alkyl group that you're naming, and the other side is coming from acid. So if we name this compound as isopropyl group, and then it's coming from formic acid or metanoic acid, so you would just say metanoate. So isopropyl metanoate. And the next example, so one part of the molecule is coming from alcohol, the other side is coming from carboxylic acid. How would you know which side is coming from alcohol? The side that is attached to oxygen is coming from alcohol. So this is the R prime that is coming from alcohol, and this is the R coming from carboxylic acid. R is attached to the CO double bond, and the R prime is coming from alcohol. So when you say alkyl, you are going to name the side that the R group that is coming from alcohol. So it's a phenyl group, and then this part, if you add a hydrogen, the name is going to be benzoic acid, but when you are naming as the ester, you would drop the ic acid and you add ATE. So benzoic acid would change to benzoate. So phenyl benzoate. Now, in this case, what is the name of the alkyl group? I hope that by this time you already know the alkyl group is the methyl, and then this part is going to be named as the acid, but you drop the ic acid and you add OAT. Now, to name this part as acid, you have a combination of open chain and a ring. And the open chain carries the functional group of carboxylic acid, so it would take the priority. So we have 2 carbon with the carboxylic acid, so that would be ethanoate. If it's 2 carbon is ethane, 2 carbon carboxylic acid is ethanoic acid, and as the ester, you would take the ic acid out and add ATE. So we have ethanoate. When you say ethanoate, it covers this 2 carbon and the COO. The CH2CO double bond CO single bond is covered by ethanoate, but the phenyl group that is attached to carbon number 2, because that would be carbon 1 and this is 2, needs to be added. So it's going to be 2-phenyl ethanoate. Okay, 2-phenyl ethanoate. So this part of the name is coming from the carboxylic acid part, and then Methyl is coming from the alcohol, so it would be methyl 2-phenyl ethanoate. So alkyl, alkylate. Cyclic ester. How do we know this is ester? If you have a CO double bond or single bond, this carboxyl group attached to 2 carbon or 2 R group, that is ester. And this is a cyclic form, so it's going to be a cyclic ester. A cyclic ester is named as the original what is coming from, okay? What was the original carboxylic, the open chain acid that had formed a cyclic ester. In order for cyclic ester to form, is the requirement is that your molecule must have carboxylic acid functional group, and it must have like a OH functional group. So alcohol and carboxylic acid are on the same molecule. If this is the case, and you catalyze this, bring acid and heat, is going to make the OH leave, and then the alcohol branch is going to form bond with this carbon. So there would be a new bond forming between the oxygen and carbon. So you have 1, 2, 3, 4, and then 5 would be oxygen. So it's like a 5-member ring is going to give. When it comes to this molecule that we have here, we basically have to break between carbon and oxygen single bond, add OH to this side, and add H to the oxygen. So that's how we open the ring. Because if you break the bond between the alcohol and carboxylic acid, or if you hydrolyze ester, it would give you carboxylic acid and alcohol. And how it's going to happen, you basically break the bond between carbon, oxygen single bond, add OH to the carbonyl group, and add H to the oxygen. So if you open this chain, you have how many carbons? You have 1, 2, 3, 4, 5 carbon. So basically, I'm going to draw that COOH here, and add 5 carbon, 1, 2, 3, 4, and 5 carbon. So OH is attached to carbon number 5. So now we have to name this and add name of lactone. If you add lactone, that means that you started with this compound, but change that to cyclic ester. So you first name this compound, and to name the compound, you numbered 1, 2, 3, 4, 5, and then you have OH group on carbon number 5, so it's going to be 5 hydroxy, pentanoic acid. That's what we have, pentanoic acid. That's for open chain. But this compound, if you want to name this compound, you have to add the word lactone. So you first open the chain or the cyclic system, open it to open chain, carboxylic acid and alcohol, then name it as acid, add the word lactone, and that would be, IUPAC naming for that. So I am not going to add the common name because then it would be like too much. But if you like to learn about the valeric acid, so valerolactone, valeric acid, that's carboxylic acid with 5 carbon. So you have another example. So just know about the IUPAC name. You should be fine. For the other example, we follow the same procedure. The same procedure is to open this carbon the cyclic system from carbon-oxygen single bond. You break the carbon-oxygen single bond. You add OH to the carbon, and you add H to the oxygen, then number it 1, 2, 3, 4. Okay, because you don't have to number the oxygen, so you have like 4 carbon. Then you draw the open chain. It takes time, but it's best is you're not going to make a mistake. So it's going to be 1, 2, 3, and 4. So you had 4 carbon, and in the cyclic system, you put the 4 carbon in open chain. Then any branches you add. So there is the methyl group on carbon 2, so you'd add the methyl group to carbon 2. There is a methyl group on carbon number 4, so you add the methyl group to carbon number 4, and that is going to make it 5. So 5 carbon, because the methyl group is attached to carbon 4. And then there's the OH group attached to carbon number 4. So you name this carboxylic acid, and in order to name this carboxylic acid, you have your 5 carbon acid. First, you give the branches in alphabetic order. So it's going to be 4-hydroxy, 4-hydroxy, and then you have 2-methyl. 5 carbon is going to be pentanoic acid. Pentanoic acid. So this is the name for this open chain acid that was used to make this cyclic system. So if you were going to name the cyclic system, you have to name this acid first and then add the word of lactone. That means cyclic ester. Okay. Amides, that's another acid derivative. Amide, the leaving group or the functional group that you have here in the amide is the N, the CN, or the amino group. If the molecule has only 1 carbon nitrogen, is going to be primary. If it has like 3 carbon nitrogen, is going to be tertiary. If there is 1 hydrogen and 1 carbon here, there's a carbon there, then it's going to be secondary. So it depends on how many carbon nitrogen bond you have in the molecule is going to determine the degree of the amide, primary, secondary, or tertiary. What is unique about amide is that in amide, you have pair of unshared electron in nitrogen, and that is conjugated with a pi bond. So you have this possibility for formation of resonance. The pair of electrons is going to drop in, and as soon as the pair of electrons drops in here, this carbon that already has 4 bonds, pi bond has to move up. So pi bond would move up and gives negative charge to oxygen, and you get formal charge of positive for nitrogen. So one of the resonances of amide, so you have 2 resonances for amide, only 2 resonances for amide. So you could have like a 50% of left, 50% of the right resonance at any given time. So it is going back and forth. When it's in this form on the one on the right side, it is acting like an ionic compound because you have a plus-minus charge in the molecule. And what makes this unique is that is going to make the amide with the strong intermolecular forces is going to make it give you the highest boiling point due to the strongest intermolecular forces, because 50% of the time is acting as ionic compound. So if you compare the boiling point or melting point for amide compared to other molecules from other families of organic compounds, amides, they would have extremely high or expected high melting point or boiling point, and that is all due to this positive and negative charges that you have in one of the resonances. The pair of electron and nitrogen, it can be also used to do the protonation. The double bond of the oxygen, the CO double bond, would get protonated under the acidic condition. So you have a protonated amide. Okay, when you have protonated amide, now with the protonated amide, you can actually give better chance for the reaction, because amide itself is not very reactive. So if you were going to like hydrolyze or do any of the reactions, is going to require acid catalysis, or it would be catalyzed. About the classification of the amide, I did mention it. If you have one CN bond, is going to be primary, and if the hydrogens are from the NH2 is replaced by more alkyl group, then you would see increase in the degree. So you have a secondary here, because you have, here's one and second CN bond. For tertiary, you have three CN bonds, so that makes it tertiary amide. So we have primary, secondary, or tertiary amide. In the for tertiary amide, you see that there are two alkyl groups attached to the nitrogen. In secondary amide, there's one alkyl group attached to nitrogen, and for primary amide, there is no alkyl group attached to nitrogen. When you are naming amide, well, when you say amide covers the CO double bond and N. That's amide. It doesn't cover any alkyl group that is attached to the nitrogen. So you have to make sure you count those as branches. When you are numbering, you have to start from the carbonyl, and you have to, because you're numbering carbon chain, you cannot go to right in this case, because if you go to right, you're gonna hit the nitrogen. You're looking for carbon chain, and you always start with the carbonyl group for the acid derivatives. So you have 1, 2, and 3. So when you say propanamide, that means 3 carbon, CO double bond, nitrogen attached to the CO double bond. This part is propanamide. And if there is a methyl group on the nitrogen, you would say, you have to name that. If the alkyl group is attached to the nitrogen, you don't use numbers. You just use N, and you treat N as a number. So you would say, like in this case, you would say N-methyl, and there is an N-methyl, one more N-methyl, so it's going to be N-dimethyl. Or in this case, for secondary, you have a methyl group attached to nitrogen, so it's going to be N-methyl when you are naming the branches. So in this case, for the secondary, you have 1, 2 carbon. So if it's 2 carbon, and you want to say 2 carbon is going to be ethane, there is the amide functional group, so you would say ethanamide. And then acetamide is like a common name, but ethanamide is going to be IUPAC name. So you have methyl group attached to nitrogen, so it's going to be N-methyl ethanamide or acetamide. It's a common name. Ethanamide is easier for you, just be consistent and know the IUPAC name. So let's look at this molecule here. In this molecule, for the nomenclature, for this molecule, we are starting with carbonyl carbon as carbon 1. We cannot go to the right side because it's nitrogen. We have to go to the left side, 1, 2. And then which one gives us the longest carbon chain is going to be the same. So if I go down or if I go left, it's going to give me three carbon only. So in this case, I have only one methyl group here. So one methyl group that did not take a number. So I have a 2-methyl. The methyl group attached to nitrogen didn't take a number, and an ethyl group attached to nitrogen did not take a number. So since I have 3 numbers or 3 carbon here, with the carbonyl and the nitrogen, so this blue box here, okay, the blue box, not including the CH3, is going to be propanamide. So we have propanamide. With the propanamide here, then we have methyl groups, 2 methyl groups. One is on N and the other one is on carbon 2. And we do have a N group on the nitrogen also. So when we name it, we are going to say N-ethyl, alphabetic order, N-ethyl, N-ethyl. And then we have 2 and N. So comma, 2, N. N is treated like a number, so use a dash after that. So it's going to be 2N dimethyl propanamide. Okay, N-ethyl 2N dimethyl propanamide is going to be name of this amide. So let me see if the name here, it didn't sound correct to me. So you have the N-ethyl, N-methyl, and then 2-methyl propanamide. So there is no di here. You cannot say N-methyl and then 2-dimethyl. So because on the carbon 2, we only have 1 methyl group. This carbon adds to the chain. So there is a typo here. Make sure that you make a note of that from the PowerPoint. So it's 2, and you can, because it's the methyl group, both N and 2, you can combine it. It's going to be 2, N dimethyl propanamide. For cyclic amide, they are named as lactam rather than lactone. So we name it as the lactams. So for the lactams, you are going to break the bond between C and single bond. So CO double bond and nitrogen, you break the bond, you open the chain and say that this compound was coming from 1, 2, 3, and 4, and there's an amino group attached to carbon number 4. So it's a 4-amino butanoic acid. So that's the name. So on the product, or when you have the cyclic lactam, you would say 4-amino butanoic acid lactam, just like cyclic esters. So, but there we have lactone. For amide is lactam. Nitrile, when you hydrolyze nitrile in acidic or a basic solution, is going to give you carboxylic acid. Okay, carboxylic acid, and then it will give you the byproduct of ammonia. Yes, byproduct of the ammonia. So you get carboxylic acid as a result of hydrolysis of nitriles, and that's why nitrile is going to count as acid derivative. So because they can be hydrolyzed to carboxylic acids. When you are naming nitriles, you would name it as as just the you add a nitrile to the end of the name. So if you have two carbon, so um, ethanonitrile or acetonitrile in this case. But if you have a CN group as part of the carbon chain, that you also have a carboxylic acid. So in this case, you would name the compound as carboxylic acid. So you would name the nitrile group as the branch. So it would be cyano group. And if the nitrile group is attached to a cyclic alkane, so it's going to be cyclopropane carbonitrile, because if you just say nitrile, if you say cyclopropane nitrile, that means you're not counting the carbon. So you're missing one carbon, and there is no cyclic nitrile. If you say cyclic nitrile, that means you're giving like 5 bonds to the nitrogen. There cannot be a cyclo nitrile. So if you have like a cyclic nitrile here, which does not exist, you're giving 3 bonds, and 2 is going to be 5 bonds, and that doesn't exist. But you could have a cyclohexane and then carbonitrile. Acid halide or acid chloride, it's coming from acid name, and then you add chloride. So instead of the ic acid, you are going to change that to il chloride. Okay, so if you have 3 carbon here, 3 carbon acid, 1, 2, 3. If you had the OH here, it would be propanoic acid. So you drop the ic acid, and add il and then chloride. Okay, propanyl chloride. 1, 2, 3, 4. 1, 2, 3, 4. This bromine is going to be named as bromide. So that's this bromide. But this bromine is as a branch, so it's going to be bromo. So the only one that is the halide or chloride or bromide is the one, the halogen that is attached to CO double bond. So you have a bromo and then a butanoyl bromide. So you drop the ic acid, add il and halide. Acid anhydrides, they are, for acid anhydrides, is like 2 carboxylic acid group combined and by losing of water. So it's the 2 molecules of carboxylic acid lost water changed to acid anhydride. So let me just draw this structure here. Let's say you have acetic acid here or ethanoic acid, and then you have another ethanoic acid here. If you, in industry, it would be more of a heat. If you make the hydrogen and OH leave and give H2O as the byproduct, and then the new bond between this carbon and oxygen forms, and that gives the functional group of CO double bond. Then you have CO single bond, O attached to another CO double bond. That's basically what you have here as the functional group for the acid anhydride. Some acid anhydrides, they are symmetrical. You have same number of carbon on both sides, and others are not. So in this case, it's not the same number of carbon. If you had the same number of carbon, like if you have 2 carbon here and 2 carbon on the other side, this is coming from ethanoic acid or acetic acid. So you just say ethanoic anhydride. It's kind of understood that if it's an anhydride, it's coming from 2 carboxylic acid, but you don't have to repeat it, just like ethers. So ethyl ether, meaning that you have two ethyl group attached to oxygen. So in this case, it's coming from 2-ethanoic acid. But if the number of carbons are different, so they are not symmetrical, you have to give both name of the acid, which two acids they are coming from. One side is coming from ethanoic acid, the other side is come from methanoic acid. You can use the alphabetic order: ethanoic, methanoic, anhydride. That means the methanoic acid combined with ethanoic acid, lost the water and changed to anhydride. So we have ethanoic, methanoic, anhydride. So that's for the mixed anhydrides. Okay, for the solubility, acid chlorides and acid anhydrides, they are highly soluble in water. Esters and tertiary amides and nitriles are good polar aprotic solvents. And ethyl acetate, that is an ester. Amide, DMF, diethylformamide, okay? Dimethylformamide, that is DMF, or another good solvent is used, and then acetonitrile, that's another good solvent that is used, acetonitrile. So you have the acetonitrile and diethylacetamide, okay, dimethylacetamide. The acetamide or ethanamide is coming from the 2-carbon carboxylic acid. So they are going to be soluble in water, but this molecule here for ester, it is soluble partially in water, but not highly soluble. Amides and nitriles, this is because, if you remember, I said that one of the resonances is going to be plus minus. It also is going to act like partially ionic compound. And if it's partially ionic, it's going to dissolve better. For IR spectroscopy of the acid derivatives, for all of them, except for nitrile, you do have a CO double bond. CO double bond, approximate location is going to be at 1700. Now, if it's attached to electron withdrawing group, this number is going to increase. If it's conjugated, it's going to decrease. So if you look at ketone, so there is no conjugation, no electron withdrawing group, that is the normal number. For carboxylic acid, the CO double bond is going to show a peak at 1715, and then you also have a broad peak between 2500 to 3500. So that would indicate you have a carboxylic acid because you have the OH in addition to CO double bond. For ester, this number for CO double bond is going to increase to between 1730 and 1740. These are not exact number, but it's going to make a difference if you have electron withdrawing group attached to it. And if it's ester, you don't have this 2500 to 3500. You only have the peak around 1700, but because it's attached to electron withdrawing group, it's going to increase to 1730 to 1740. The number is given here is called 1735. Amides, we talked about resonance that is forming for amide, and that is going to make the CO double bond appear at the lowest, and that is going to be like 1640, 1650. But if there is a hydrogen attached to this nitrogen, so basically if you don't have a tertiary amide, the NH bond also is going to appear at the around 3300, just like the same location as the OH for the alcohol with one spike. The CO double bond for acid chloride or acid halide, because of the high electronegativity of the chloride, this is going to increase and 1780 to 1800. For acid anhydride also is going to be high because electron withdrawing group is attached to it. But what is unique about acid anhydride is that you would see like a double peak. So if it's in the, around 1780, between 1750 and the 1800, if you see like a double peak, that is coming from acid anhydride. So you have double peak, two peaks. Nitrile Cl triple bond shows a peak at 2200. This is an example for the for ester. And how do I know it's ester? Because it's alkylate, okay, is ester, and we expect a peak between 1730 to 1740, and that's the peak that it appears 1739. So for cyclic esters, okay, the ring strain is also going to affect the number for the CO double bond. The more relaxed or more stable one is the 5-member, 6-member. Then if it's like a 4-member, this number is going to increase. So the ring strain is going to increase the frequency for the carbonyl stretch. So just keep that also in mind. Even for the amide, if you have a 4-member ring, it's going to be higher than 1700. For 5-member ring is 1700, but for 6-member ring is 1670. So the ring strain is increasing the frequency for CO double bond. Proton NMR absorption for the for alpha carbon, which is a carbon, or the alpha hydrogen, which is the hydrogen on the alpha carbon. And what's alpha carbon is the carbon adjacent to CO double bond. That is going to be increased. If you have a carboxylic acid, it's going to happen between 10 and 12. And if you have any electron withdrawing group attached to the carbon, carries the because the functional group for the acid chloride in this example itself doesn't have any hydrogen. So we are talking about proton NMR. There would be no signal coming from this area of the molecule, but the adjacent carbon is going to be affected by the electron withdrawing property of CO double bond attached to highly electronegative element, because the more positive this carbon is, more deshielding is going to happen on the adjacent carbon, and it's going to shift to higher number. For for ester, the carbon that is attached to oxygen single bond is going to, because it's a direct effect, this oxygen is on the same carbon that you have the hydrogen, it's going to be between 3.5 to 4.5. And then for amide, the NH bond, just like amines, it can vary. It's not, but it's at a higher number, because for amines, the NH is going to be anywhere between like 3 to 7. But for amide, the NH is going to be between 5 and 8, slightly higher than amines. And the CH2 or the hydrogen adjacent to nitrogen, this nitrogen is acting as electron withdrawing group, is going to increase also. We already know about aldehyde. And for the formate is going to happen at the, for this hydrogen attached to the ester functional group directly, because it's on the same carbon, but it's very positive. It's more positive than the CO double bond. It's going to be around 8. For formamide and formate would be 8. And then for nitrile, the nitrile doesn't show any group, any peak in the proton NMR because there is no hydrogen on the nitrile, but is acting as electron withdrawing group. So adjacent carbon, the hydrogen on adjacent carbon is going to shift to higher number. For carbon-13 spectroscopy, carbonyl group would appear in higher than 160, between 160 and 200. And the other carbons depends on how deshielded they are, is going to happen at the higher numbers. The more deshielded, it would happen at the higher number.